Next, Tim will describe different types of control technologies and emission reduction programs for stationary, area, and mobile sources.
In this presentation, I want to give a fairly thorough overview of candidate stationary, area, and mobile source control measures. In so doing, and even though I'm going to give you lots of examples of candidate control measures, it's important to note that this isn't an exhaustive list. In fact, EPA expects that as states work on their state implementation plans and interested parties provide feedback on those plans, there will be a continually updated database of information with respect to control measures, and we want to promote information sharing and do what we can to summarize the information that is available. I'm going to talk about point source measures for direct PM 2.5, SO2, and NOx, a few general issues with respect to that, and I want to talk about some category-specific measures that we're aware of. I want to talk about the available controls for a few categories of area sources which are being controlled or regulated by state agencies. And I want to provide some summary information on mobile source measures that are summarizing information from our Office of Transportation and Air Quality. So I'll start with point sources and give you a few personal observations with respect to control measures for direct PM. Direct PM has been regulated in some form since the inception of the Clean Air Act, and even before that with state programs that preceded the Clean Air Act. You know, historically, a lot of the early efforts on air pollution control were aimed at visible emissions and preventing smokestack obvious pollution sources. So direct PM has been controlled in some form for many decades. Typically, what I would call Method 5 or total particulate has generally been the focus of programs. So really, against that background, we're now asking the question, how is fine PM different from PM10 or total PM? Completely uncontrolled stack sources, in my judgment, are relatively rare. So methods to achieve further reductions in the fine fraction may often include the following: improving the performance of existing control devices, taking action to improve the particles that are captured and thus collected by control devices, identifying and mitigation of the malfunction of processes and equipment, and upgrading control devices to improve the degree of control efficiency those control devices will achieve. Often, the analysis of the impacts of those types of measures really are, in my judgment, going to involve case-specific engineering studies at a plant, rather than applying some generalized control percentage to an emissions inventory category. Many of you familiar with SIP analyses are familiar with analyses which look at applying a type of control to a certain, say, SCC category, using that as the basis for modeling. I think it's a little more complex when you're dealing with direct PM for the types of things I just described. And an emissions inventory is likely not detailed enough to evaluate whether, for example, a control device is undersized, whether the fine fraction could be controlled better with equipment upgrades, or whether the plant has a configuration that would allow for increased capture of pollutants. But nonetheless, it's important to note that the information that is there indicates that there are design value monitors for which point sources are likely an important part of the non-attainment plan analysis. This slide indicates the location of the Dearborn, Michigan monitor relative to nearby point sources. This slide indicates pollution rows information shown in the lower left-hand corner, which indicates that point sources near this Birmingham monitor are likely contributing significantly. OEQPS funded a report that was completed in 2005 in which a contract study looked at ways to improve the performance of control devices. And that report has a pretty good summary of the types of improvements that you may want to take a look at. Since that time, more recently, the Institute of Clean Air Companies provided us with a summary of 16 technical papers that described ways to improve the performance of ESPs and fabric filters and other types of devices. I have a CD with the complete papers for that, and if anybody contacts me, I could certainly provide you with a copy of that. There's two broad types of control device improvements that are mentioned in the contract report and in the ICAC information. First of all, improvements to existing devices, and secondly, what might be called innovative technologies or innovative upgrades. Examples of improvements to existing devices would include improved monitoring, conditioning agents, modifications such as, say, upgrading the size of an electrostatic precipitator, gas conditioning, certain types of internal equipment replacements at electrostatic precipitators. Those types of things can improve the performance of these devices. For fabric filters, improved fabrics can sometimes lead to better performance and fewer malfunctions. For wet scrubbers, increasing the pressure drop is certainly a way to improve the performance. Reducing the temperature of a process stream and a vent stream can lead to condensation of the condensables and therefore being in the particle form when they see a control device, and therefore reducing the temperature can lead to better collection of condensables. This slide indicates a document EPA put out in the 90s talking about bag leak detectors as a way of determining in a more expeditious way when fabric filters are malfunctioning and thus reducing emissions. The second type mentioned in the contract report was innovative PM 2.5 controls. This is not sort of just changing the device in a minor way, but it's kind of entirely different technologies. For example, COPAC, a compact hybrid particulate collector, is essentially a polishing filter with a relatively high air-to-cloth ratio that can collect fine PM 2.5 downstream of an existing electrostatic precipitator. Another example of an innovative technology is the indigo agglomerator, which is basically an upstream modification to an ESP, which applies an upstream charge to increase the size before it sees the ESP, therefore allowing that ESP to do a better job at collecting particles. Certainly another example is a wet electrostatic precipitator. Now I'm going to talk about certain individual source categories and some candidate measures that have been mentioned for those categories. And I'll talk about iron and steel mills. I'll talk a little bit about stationary diesel retrofits. And I'll talk a little bit about a few categories that emit SO2 besides utilities. Within the last few years, upon request of Michigan, our office funded a multi-pollutant controllability study at 2 Detroit area steel mills and a coke oven facility. And the contract report for that study is available. And what it found was there are possible additional control measures at the blast furnace cast house by increasing capture at the basic oxygen furnace area. And the study also recommended possible improvements to collection efficiencies at certain control devices. The study identified coke oven gas desulfurization as a way to readily reduce SO2 emissions and also recommended further testing with regard to the condensables at the coke oven combustion stack. Other possible measures for steel mills identified as a result of this effort were NOx combustion controls and PM controls from cinder coolers. So as a result of the Detroit study, in taking a look at this, it could be that other steel mills may be candidates for a case-by-case analysis to see if some of the measures that were identified in the Detroit study might also apply to those plants. Second category I want to talk about is stationary diesel retrofits. There's many retrofit programs for mobile source engines such as buses and trucks and the like. And essentially these same engines, these are very similar to the engines that are used for stationary source applications. And the same types of devices would apply, such as diesel oxidation catalysts and diesel particulate filters. And typically, diesel particulate filters that have only been applied to relatively recent model years of diesel engines, and oxidation catalysts can go back a few more years than than DPFs. But generally, the verification process and the verified technologies are looking from roughly the mid-90s on. One pilot study that our office is funding is looking at whether a diesel particulate filter with a case-specific design and certain modifications can be engineered to work on much higher emitting 1970s engines. Stationary diesel retrofits are the subject of a lot of discussion on stationary diesel exhaust within our office. And Chris Stoneman of OQPS is the contact on this. And we're currently in the process of deciding what actions the agency might take in response to a 2003 petition from Environmental Defense. Okay, now I'm going to talk a little bit about point source sulfur dioxide and the controls that might be candidates for a PM SIP for SO2 for these sources. Industrial boiler controls include flue gas desulfurization, fuel switching. In some cases, industrial boilers burning distillate oil may be able to reduce the sulfur content of that distillate oil, which, after all, is very similar to diesel, except for the way that it's dyed and taxed. For petroleum refineries, control measures were identified, have been identified in enforcement settlements. And so those enforcement settlements identify sources such as scrubbers for fluid catalytic cracking units, increased recovery of sulfur at sulfur recovery plants, therefore leading to lower SO2 emissions, and ways to lower emissions limits for process heaters. More recently, there have been enforcement settlements within the last few months on sulfuric acid plants. Essentially, what a sulfuric acid plant does is it burns elemental sulfur into SO2 and captures that in a big scrubber. And essentially, if you increase the conversion efficiency of that process, you lower the SO2 emissions. And for example, if you take a look at the AP42 emission factors for a sulfuric acid plant with 93% conversion, such a plant would emit 96 pounds of SO2 per ton of product, whereas a source emitting that was complying with our new source performance standards would only be emitting 4 pounds per ton. And so the types of controls necessary to do that should be available from some of these enforcement settlements. The Northeast States Consortium has looked at controls in a BART review for cement kilns, and so the types of measures for cement kilns they looked at may also be candidates. I'm going to touch very briefly on point source NOx controls, although NOx will certainly be a precursor to PM that will be looked at in many PM fine SIPs. Much work has already been done on NOx controls for ozone, and I would suspect that many viewers of this will be familiar with those controls. The types of references on the website that I mentioned include ACT documents and the like. The technology continues to advance for NOx controls. If you want information up to the moment on where the technologies for NOx are with cement kilns, you can contact Bill Neifer, who follows this closely. With EPA summaries of the degree of reductions from certain technologies for other types of NOx sources, which generally include combustion controls such as low NOx burners, and downstream controls such as SNCR and SCR. Certainly those types have been applied to a lot of categories such as glass plants, refineries, iron and steel mills, and other source categories. Another area of possible interest with regard to NOx controls is how long it would take to install the controls. And the Institute of Clean Air Companies on their website put together a white paper describing the installation times for a number of different types of NOx control technologies.